All right, hey guys, I just want to go through this magnetism free response question. This is from the 2014 AP exam. I just want to go through kind of how I worked through it and just some of the ideas. So first off, before we go through some of the questions, with the diagram right here, some important things to know. So we obviously see a parallel plate capacitor here. We see a magnetic field indicated by B that's going into the page, because we can see the tails of the arrows that are going into the page. And then we see here our battery, right? And so if we look at this, remember that the long side is the positive side, the short side is the negative side of the battery, which means the electrons are flowing from the positive into the negative, right? So that's going to give my top plate of my capacitor a positive charge, and it's going to give my bottom plate a negative charge. Okay, so going through the problem, it asks, explain why the particle moves through the parallel plates undeflected in terms of the forces exerted on the particle. Basically, here's what I did. We don't really know at this point, or it doesn't ask us to identify which one is positive or which one is, or if it's positive or negative. So basically what I said is that there must be two forces acting on it, right? There is a magnetic force acting in one direction and an electric force acting in the other direction. So we could have where magnetic force is up, electric force is down, or the opposite, electric force is up, magnetic force is down. Basically, for the particle to be undeflected, for it to move straight through, the net force must be zero, Newton's first law, right? An object will stay in constant motion as long as the net force is zero. This means the electrostatic force due to the plates and the magnetic force due to the charge moving through a magnetic field must be equal in size and opposite in direction. Part B then asks you to find the sign of the charge on the particle and to justify your answer. So basically what I said, if it was negative, right, so if it's a negative charge, based on my top plate being positive, my bottom plate being negative, the electric force would be up. The magnetic force would be down due to the left-hand rule, right, because it's a negative charge. If it's a positive charge, it would still work out, right? My magnetic force would be up due to the right-hand rule. My electric force would be down. So it would still be a net force of zero, right? So we'd still have that zero deflection, which is good, but if we look at the second part of the motion, we see a circular arc going downward on the page. Right? So what I said was the particle must be a negative due to the path taken after it leaves the plates. For it to take a circular path downward, FB must be downward. All right? And you can only get that by using your left-hand rule, which gives it a negative charge. Okay? The second part then asks you to do a few calculations of the different components. Right? And the big thing that it tells us is the particles reach the collector plate a distance of 0.42 meters below the point where it left. So the big thing to point out, this is the diameter of a circle, right? So that's 2r, right? In terms of the geometry of the circle. Okay, so basically the first part, it wants you to find the potential difference between the plates. If we have the electric force and the magnetic force equal each other, we have charge times electric field equals QVB. Charges go away. We can then replace electric field with my potential difference divided by my distance, which equals V times B. And I can solve for my electric potential there and get 3,000 volts. Part D wants you to analyze the circular part of the motion and using that to calculate the mass for the particle. So we lose the electric force. It's only the magnetic force, which is QVB. It's a circular force, or it's pulling the particle in a circular motion. So that means, based on mass times acceleration, it's mass times v squared over r. I'm going to replace r with d over 2, right, or half of my diameter. And then I'm going to kind of do a little bit of algebra and solve for m, right? I get v on the top, v squared on the bottom. So I can cancel one of those out. And I'm left with charge times magnetic field times distance divided by twice my velocity. And from that, I get 5.04 times 10 to the negative 27 kilograms. The last part, it wants you to identify if someone is trying to separate carbon-12 and carbon-14. Describe how the motion of these isotopes will be in both regions, right? And identify how we'll be able to separate them. So first off, when the two isotopes travel through the plate region or through region 1, basically, because we saw that the electric force and the magnetic force, when they are equal to each other, the charge plays no factor. There is no mass playing a factor. It's only dependent upon the charge's velocity. So because they're both going to be coming out at the same velocity, then they will still take the same path. So there'll be no separation for that first part of the motion. However, in the second region, when we're outside of the electric plates or the parallel plates, the distance that it's actually going to travel, that diameter of that half circle, is going to be equal to, and I took that just from this equation here, I rearranged it for D, is going to equal twice my mass times velocity divided by charge and my magnetic field. So because carbon 12 and 14 will have a different mass as well as a different charge, they will have different diameters, right? And so that's where you're going to get that separation of carbon 12 and carbon 14. Both charge and mass play a role in the path it takes, and that's going to separate them into different paths.